We have joining us today, we've got Joe Schoonover from Fluid Numerics. And hi, Joe. So Joe is a scientist and research software engineer at Fluid Numerics. He has a PhD in geophysical fluid dynamics and held a postdoctoral research position at Los Alamos National Laboratory Center for Nonlinear Studies. Joe's current research focus is in spectral element methods, physical oceanography, and environmental fluid dynamics, and he has a continued interest in portable GPU programming and scientific application modernization. Many of you know Joe, so he'll be talking to us today about his takeaways from the 2022 PACER mentored sprints, and many of you have worked with him on that already. So Joe, you're well known, and your name has been coming up repeatedly over the last 3 days, so your ears must be a bit burning at the moment. It's evening, so thanks for joining us as well.
I was wondering why my tinnitus was acting up this week, so let me see if I can get the screen share up here. Boy, I wish I could be there in person with all of you. Looks like a fun time. So yeah, today I'm going to just kind of provide a summary for everyone of what we were up to this year with the mentored sprints. For some of you, portions of this talk will be very familiar. We've hashed over these things numerous times in our retrospectives and things like that. But I hope that this gives you a broader picture of the various teams' activities as we all get ready for Photonics. So of course the goal of the mentored sprints was to help you all get ready for the upcoming AMD GPUs on Photonics. And in case there are some of you here who have not participated in a sprint yet, the mentored sprints each take place over a 5-week period. We dedicate the first 3 weeks to developing a plan so that we can have a very productive 1-week sprint and make some progress in getting you guys ported over to the AMD GPUs. On that first 3 weeks, there's a lot of preparation and planning that happens. Of course, there's establishing which compute platforms we'll be focusing on. Given that a lot of applications are already running on the NVIDIA GPUs, of course, we have to kind of look at hopefully getting on 2 platforms. And for the most of y'all, we've been working on Topaz, which has the NVIDIA V100s, and Mulan, which has the MI100s. And then we'll spend a good deal of time reviewing software application and assessing some of the goals that you all set out and try to come up with a coherent plan and break out tasks so we can work towards meeting those goals as a team. I know a lot of that involves, getting application profiles, coming up with some kind of development strategy, branching models, things like that, so we can work collaboratively together, as well as coming up with very concrete descriptions of how we're going to build your code and how to test it. And all that comes together in terms of a final sprint plan, which is then preceded by 5 days of sprinting activities. And if you've participated in hackathons before, the sprint week is much like a hackathon, except with just one team. We usually meet once a day to just sync up with each other, talk about progress, and address any hurdles anyone on the team is coming up against. And of course, in the meantime, we can chat through other services like Slack or Microsoft Teams or email, just to keep things moving along. At the end of the sprint, we'll usually develop a retrospective report that summarizes what we originally planned, what we actually ended up doing, any lessons learned in future directions, so that you leave the 5 weeks with somewhat of an accurate description of what actually went on and where you can go. So for this year, we worked with 5 different teams so far. Some of you may recognize your own team up here. At the moment, we had XS kicked everything off earlier in the spring. I guess spring for Northern Hemisphere, so fall for y'all. And then we went on to MCCC, GTX Hipstar, Viscus, and ASCAP. ops. We had a mix of languages, of course, C, C++, and Fortran, compiled languages being represented. And basically, we had a handful of codes starting from CUDA, some starting from OpenACC, and trying to make their way over to HIP and OpenMP. We had one team participated on the Viscous side. They're working in Lamps, who is developing some new features with Cocos inside of Lamps, and of course, target GPU API there's Cocos, which is quite nice. So what we'll be doing here today in this talk is just kind of going over the highlights from each of these teams, and hopefully you guys find any of this interesting and have questions along the way. All right, so with XS, so XS is a quantum chemistry code. It's written in C, C++. It is an MPI plus code. It can basically interoperate between MPI and OpenMP for multi-threading, or using CUDA for multi-GPU applications. The key spots in the code we focused on were on what are called these recursive integral calculations, which were being used to form matrices that we were doing eigenvalue decompositions on. So there's two spots there in the code that we're going to focus on in the next few slides. You'll see how that played out. And we started off with the three goals of getting the CUDA portions of the code ported over to HIP, which is actually fairly straightforward. And we had this initial goal of trying to at least match the V100 performance on the MI100s out of the box. And I'll show you in the next slide why that's actually quite a reasonable goal to try to achieve. And initially, we were trying to look at assessing if there was any room for improvement on the kernels by using roofline modeling. And on the systems we were working on, we were using the ROCm 4.5. I think I caught the last tail of the discussion there. Tom was talking about the roofline modeling that's now capable in ROCm 5. In ROCm 4.5, there were some limitations on the hardware performance counters that prevented that last bit there. Now, in terms of it's a comparison that you might want to keep in mind, you probably have seen some of this already. But between Topaz and Mulan, what we can do is run some empirical measurements using a micro benchmark called MixBench, which will go through and run kernels of varying arithmetic intensity numerous times, and then report out of course, the runtime, which you can back out from that the flop calculation. In these micro benchmarks, the Econdis MixBench, you have some awareness of how many flops you're actually doing, how much data you're doing. So if you have that in the runtime, you can empirically recreate what the roofline or the achievable roofline could be for each piece of hardware. Now, if you compare the theoretical specifications for the NVIDIA V100, global memory bandwidth of about 800 and change gigs per second, and a peak 32-bit flops of about 14K. Sorry, that's 14 teraflops there. And then the MI100, there is on the theoretical side, an estimated potential gain for performance from migrating from V100 to MI100, provided your application is suitably optimized. Now, the micro benchmarks, that same kind of story plays out, where you see in green is the V100 achieved performance for varying types of floating point operations. We have everything from FP16 to FP64. And then the various red dots are showing the AMD MI100. So these are all just empirically measured roofs. So the thinking being that if you were to take your application, if it were sitting on one of these roofs, and you were to migrate to another piece of hardware, you would be able to realize those particular gains when you move to the new hardware. So here what we're showing is just to lay out sort of what we observed in terms of performance when we initially did the port. So the porting process itself was actually fairly straightforward. Now, the code did have a lot of methods for generating kernels. So there was like a templating routine that they would run to generate a whole slew of kernels for doing these various recursive integral calculations. Getting that converted to HIP was not really hard because the syntax is exactly the same. So most of the stuff that had to swap out in the code was like the malloc, the CUDA malloc calls, CUDA memcopy, etc. And that was handled pretty straightforward with the Hipify call. So what I'm showing here is screenshot of a trace profile generated from Rockprof on Crusher over at Oak Ridge, which is the MI250X platforms, and it's visualized with Perfetto for one of the benchmarks that we were looking at. Now the top half of the diagram shows the timeline, which is the trace profile, advancing with time advancing from left to right. And if you zoom in on a particular region, so basically what you can see here is we're running multiple iterations of the exact same kernel just to get a reasonable estimate of what's actually happening in a single iteration of this code. Zooming in on a particular region, the main two spots where the code's spending most of the time is actually doing hit mem copies, asynchronous mem copies, and then as well as one of these integral calculations. On the MI100s on Mulan, we see a very similar behavior. Of course, the kernel runtimes are a little bit slower. There's some other bits here that we could talk about later if you guys are interested, but there are some gaps in between when kernel launches are issued and when kernels actually run, and same thing for the mem copies that we found quite odd on the MI100 systems. But the takeaway here is that independent of these two platforms, the two main things that are eating up most of the time for this particular application are the hit mem copy calls and this integral kernel. So we're going to look at just those two comparisons. Again, all we've done from the original starting version of the code was run through the HIPification process for the API calls, and the kernels were left identical to what they were on the V100 systems. So on the right here, we're just showing what the average runtime was for the mem copies up top and that single kernel that we were particularly interested in. When we go over to the MI200s, we actually saw a slowdown by about a factor of 2 with just no tuning for that particular kernel launch, and then running on the MI250s, again, no changes. That the runtime just goes straight down. Now, most of the efforts we spent on this week was getting over to the system, making sure we have correct answers. So this was just the first glance of how things do as we just vary between different target architectures. Now, I think the more interesting result we got out of this one was just trying to understand how some of these libraries behave for doing linear algebra type stuff. So in this case, the eigenvalue decomposition. So originally the code was using a CUDA solver in the back end for doing eigenvalue decomposition. So when we swapped that out, what got put in there by the HIPify script was RockSolver. And this was actually quite slow. If you were just to benchmark that particular section of code, we're looking at about 1,000 seconds to do the eigenvalue decomposition. And working through this, there's a few options out there for doing these kinds of operations. One of them is Magma, and another one I'll talk about in a little bit is Slate. In this case, we switched over to Magma and immediately saw performance improvement. And there's a pretty obvious reason why. If you do a hotspot profile on this region of code, and you look down inside of the what RockSolver is actually spending all the time on, there's a kernel that's called SteadC kernel, and you can do a quick Google search for this, and immediately this particular issue pops up on the RockSolver repository. Essentially, what's happening inside of SteadC kernel is the kernel's only expressed to have block level parallelism. They only have they run this kernel with a single GPU thread per block. So it's actually quite slow. So at the end of the day, there is room for improvement in that library. As Rockham matures, the hope is that these kinds of things get resolved. Now, of course, in the meantime, the easy recommendation is just to use something like Magma or Slate that has gone through and properly exposed parallelism in some of these algorithms. I point this out because SteadC kernel happens to be a core level routine inside of RockSolver that's used in a lot of different methods inside of RockSolver. So that was honestly the biggest takeaway for very minimal changes to our process. Just to swap out with a different library, it certainly makes quite a bit of difference. Okay, so we'll move on to MCCC. So this MCCC is a quantum scattering code. It's written in Fortran. It has a mix of OpenACC and CUDA Fortran. And it, of course, was using the PGI and NVHPC compilers to start. And then there are sections of the code that are doing matrix inversions with things like LAPACK and ScalaPack. Now, all the stuff on the LAPACK, ScalaPack side were running on CPU only. The other bits of the code were all GPU accelerated. There's really two main sections of this code. One is where they're forming a matrix based on physics. And then those matrices get passed, those dense matrices, which are fairly large, get passed off to LAPACK or ScalaPack, depending on build options. Two main goals. We established at the beginning of the sprint. First is to transition OpenACC over to OpenMP. And of course, in this process, we were actually interested as well in looking at how the Cray compilers would handle the OpenACC performance on the AMD GPUs. The other half of it was we were interested in getting the LAPACK and ScalaPack portions of the code ultimately running on the GPU platforms as well, so the rest of the code could be fully resident on the GPUs. And I'll explain in the next few slides why that was a little bit challenging. The OpenACC to OpenMP process itself was fairly simple. So there's a handful of tools out there that are quite helpful in automating the process of translating OpenACC intrinsics to OpenMP. A lot of them are basic, like search and replace style tools that leverage a JSON or a YAML dictionary to handle that mapping. The one we use here, ACC to OMP, is one of those. There's a new tool coming out called CLAC. It's based on the Clang compiler that helps do a lot of that translation, and it's a bit more robust. But this turned out to work just fine for the most part, with a little bit of hand editing, and then of course going through the make file and adjusting make flags to enable the OpenMP offloading. Unfortunately, the code uses Fortran derived types a few levels deep, and this caused both the Cray, OpenMP, and the AMD Clang, AMD Flying OpenMP interpreters to puke a little bit. But essentially where we've gotten to at this point with the ROCm 4.5.2 is that the handling of derived types and even doing things like deep copies does not seem to be supported at the moment. This issue, we've developed a minimal reproducer for to demonstrate the cause of this. It's posted online on GitHub. We're currently on our side at Fluid Numerics working with AMD to get this kind of thing resolved in future releases of ROCm. So that was a little bit of a bust. So we turn our attention to the porting over from ScalaPack to Slate. So those of you who are not familiar, Slate stands for the Software for Linear Algebra Targeting Exascale. It's developed at University of Tennessee in cooperation with the ECP project with the Department of Energy. It's intended to be a replacement, a swap-out replacement for ScalaPack. The API calls are identical to the ScalaPack calls, so that all you have to do to transition from ScalaPack to Slate is change out, how you're doing your linking stage. So you just reference the Slate library rather than the ScalaPack library during your build process, and things should just work. And depending on your build of Slate, whether you have a HIP backend or you're doing multi-threaded OpenMP backend, you should be able to target multiple platform types. So it is designed for clusters particularly, so really big problems and potentially those that may have accelerators. So like I said, in the porting process is actually fairly simple. There is just really an update to a build system to link in Slate. Now, because this application also had some LAPACK routines that are not supported yet by Slate. We had a mix of some methods still being referenced to the LAPACK routines, and some of them actually using the Slate library. On the first round, because we're using a library and there's directive-based GPU programming in the code, we broke this porting process into 2 phases after the build system update. One is just like, let's make sure we get code running on the CPU side first. And then for the GPU port, we need to look at doing some kind of tooling to interoperate between OpenACC or OpenMP and the Slate library. Essentially what that entails is finding the device pointers that OpenACC or OpenMP would create and passing those pointers off to Slate so Slate can use those in the library calls. So in that first step, this is not something we really expected, and I'm still not quite sure how to explain it. So these are all runs on Mulan, on the AMD EPYC CPUs, running on a single socket multi-core mode. Everything that's referenced on the ACC dev branch is using ScalaPack and LAPACK, and everything on this FN Slate branch is referencing Slate and LAPACK calls. There's 2 different benchmarks that were run here. This direct benchmark, there's a slight performance improvement, but not a whole lot. Again, we're still not entirely sure why this happened, but particularly you see a pronounced performance improvement on the direct plus exchange, which is a slightly larger benchmark we are running. And it's just, we cut the runtime in half. But still don't know why, because we weren't really expecting that to actually happen. But at the end of the day, by the time we got to this point, we're still getting the same answers out of the code. And so we can at least check that box. Now, in terms of doing OpenMP interoperability, which is the route we decided to start looking, we started to isolate sections of code that did not involve some of the derived types that were causing problems. And we were going to look at using the OpenMP memory management API, which is essentially OpenMP provides a few intrinsic calls to obtain the device pointers that it creates when you open up target regions on the GPU. The whole motivation for this, again, is we want to have some regions of code offloaded to the GPU with OpenMP, and then other parts of the code we want to use library calls or even use kernel, different HIP kernels that we would eventually transition some of the CUDA Fortran stuff over to. The way this would work, and this is just a real simple example, this is not from the MCCC code. This is a real simple example. You might have some host data allocated on the CPU side. You open up a target data region, and you have X and Y here, both mapped over to the GPU. You might have a region of code, just like on the premise of this motivation here, that is offloaded to the GPU. And then down below, you might have some library calls you want to make. And so the way you would handle getting that device pointer so that you could pass that address along to a library call that is GPU accelerated is you would call OMP get map pointer. You use, if you're in Fortran, you make sure you're working with C pointers. So you get the CLOC, and so that this ends up getting stored in a Fortran pointer for you underneath the hood. And then you could pass this YGPU off to, whatever method you want to work with. It could be a HIP kernel, could be a library call. Now, the downside is, when we were planning on doing this, we didn't check initially in ROCm 4.5. OpenMP 5.1 and 5.2 have very sparse support currently in the LLVM compilers. And since AMD Clang, AMD Flying Point upstream to LLVM, it's not supported in ROCm as of ROCm 4.5. Now, there's been a lot of progress they've made recently. Most of the OpenMP 5 standard is in there, so there are other less direct methods to get these device pointers out. But at the time of doing this sprint, this was looking like we hit a little bit of a dead end. Now, that being said, this spot here, this Clang LLVM website is a really good location to keep track of the up-to-date supported features in the LLVM compiler. So, you know, as these things become available, this is the kind of the direction I think this team was looking at moving towards. All right, so our third team for the year it was GTX HIP Star. This is a computational fluid dynamics aeroacoustics application. It's written in Fortran. It had a mix of regions of code that were offloaded using OpenACC. There was some CUDA as well as some cuFFT calls. So this was pretty neat in the sense that the CUDA implementation was not done with CUDA Fortran. It was done with CUDA C, which makes a lot of the porting process a little bit easier since it already, you know, the code base itself already has some kind of mixed language structure to it. And then there were some regions, actually I don't think LAPAC, ScalaPAC was in this one, apologize. Now the motifs for this application, they're mostly doing stencil operations with high order finite difference discretizations. There's a mix of Fourier transforms. And then there's a section of code where we were focusing on this Lagrangian interpolation and regridding process. So we had two main goals for the week. I say this was a big code, so we, you know, focusing even on just one of these was quite a bit of a challenge. But two main goals: get the OpenACC stuff, transition to OpenMP, and then transition to CUDA and cuFFT to HIP and RockFFT. Now, with the idea that there's still this mixed language, we have some kernels, we have some directive-based approach. We did take another crack at other ways of handling interoperability with OpenMP. As another stretch goal, we did want to take a look at this Lagrange interpolation method, which was isolated into its own mini application, so we could focus a little bit more on playing around with how much performance we can squeeze out of OpenMP, OpenACC, as well as HIP. So the porting process. So there's a couple things we needed to do here. So one, for getting OpenACC to OpenMP, because the Cray compilers do still support OpenACC for Fortran applications, and they do support the AMD backends for that. We did start with doing some hotspot profiling on both Topaz and Mulan using the OpenACC implementation that was already in there, and focusing really on the profiles for the OpenACC kernels. From here, you know, we can adjust the make system to start doing OpenMP interpretation and turning off the OpenACC interpretation. And from the hotspot profile, basically we went down a list of about 74 total 8 OpenACC kernels, and you know, just kind of ported them one by one from most expensive to least expensive. By the end of the sprint, you know, we got a little less than a third of the way there. About 21 of these kernels actually ported over, still running with getting correctness out of it, which was quite nice, but we didn't quite finish all of that work. We did spend some time porting the CUDA code to HIP, which was, again, fairly straightforward since it was mostly CUDA kernels. All those pretty much stayed exactly the way they were. The launch syntax stayed the way it was, and the really it's just the memory management API calls that end up getting swapped out. So that HIPification process, again, fairly straightforward. And then there is it was kind of neat to see the way the device memory management was done in this particular code. It was all handled in OpenACC. And whenever the code would encounter a CUDA kernel that it had wanted to launch, it would kind of decorate around that CUDA kernel these ACC host data use device directives. And when we ran through a tool, the ACC to OMP tool, to translate that to the equivalent OpenMP, this gave us an OMP target data use device pointer. So that decorator, which I'll explain in a little bit here, it does help. It basically puts in the instructions to use the device pointer in that region of code, and it is supported in the OpenMP 4.5 standard, which means it is supported in ROCm 4.5 and beyond. The challenges with getting a lot of this work done mainly had to do with just how large that code base particularly was. And then there were some subroutines that were templated, and the way they were concretized was at runtime by defining and undefining CPP flags. So it was a little bit of a challenge sometimes to figure out which incantation of the subroutine was actually running in various scenarios. But that first profile was quite interesting, just looking at using the same compiler and then just using various systems we had access to. So what we're looking at is running on Topaz with the NVHPC compilers and OpenACC coming in with the shortest runtime for a Taylor Green Vortex benchmark that we used just to exercise the code. If we run on Mulan with the Cray compilers using OpenACC, there's quite a change in the performance just out of the box. And then just for reference, having that CPU only fully subscribed multi-threaded build on Mulan as well comes in much higher. So we're still when you're running on the GPU at the MI100, we're still doing much better than the CPU only version. However, there's still a lot of room for improvement out of the box in comparison between the Cray build with OpenACC and what the NVHPC compilers can do on the V100s. These GPU 83 systems is just another reference point for V100 GPUs, the different version of the NVHPC and PGI compilers. On the Lagrange interpolation section of the code, in the last couple days, we spent a little bit of time playing around with different incantations of the Lagrange interpolation. So the way this section of their code works is there's a doubly nested loop that loops through the whole grid, and then inside of that doubly nested loop, there's a reduction operation that looks at nearest neighbor grid points and does some weighted averaging to do the Lagrange interpolation onto a new set of grid points. And so there's a few different ways we parallelized this. So we looked at doing what I'm showing here are the runtimes for our best runs and best configurations for OpenMP, OpenACC, as well as two different HIP kernels that we hand wrote. Starting off on the right-hand side, the MI100 Cray OpenMP, Cray OpenACC versions get roughly the same performance. Not really a surprise there because the directives we use essentially translate to do the exact same thing. On the GPU 83, so this is a V100 system using the same OpenACC kernels is a marked improvement. Again, this was consistent with what we saw with other sections of their code. No issue there. Now, the main difference between how we handled things with HIP versus how we handled things with OpenACC and OpenMP is the innermost reduction loop we left as a serial loop. When we wrote the HIP kernel, we actually started exposing some of the parallelism on the reduction side. So on the inner loop, the first version there is just doing a straight parallel reduction out of global memory. The other optimizations that you can implement to get reductions run faster is the typical things you would do on NVIDIA GPUs, where you do the reductions out of shared memory and then do warp level reductions out of registers at the end to get a final value. Now, the difference in performance there is about a factor of 10, which is consistent with the the difference in performance you would expect out of shared memory versus global memory. So I mean, for me, the takeaway has always been directive-based approaches can get you running very quickly. They can be nice because it limits the size of your code base. But if you really want to be able to tweak out some performance in your application, being able to get into the kernel and really tweak how things are being done, it can really make things shine. Now, I suppose, going back, one thing we did want to look at is doing OpenMP reductions inside of there on the GPU to see how that compares. But there's still quite a gap to make up there at this point. Now on the OpenMP interoperability that I was alluding to earlier, the way this can be done and the way it's done in the GTX Hipstar code now is using the equivalent of the ACC device pointer directive. So I'm showing this again, a same pseudocode example as we were looking at before. We have host side data, we enter a data region, we do some stuff on the GPU with OpenMP. And then whenever we want to use the device pointer rather than the host side copy of that data, you can actually enclose a region of your code with OMP target data, use device pointer, and you'll pass in whatever list of arrays you want to use the device version of. And so within this OMP target data and the OMP end target data, you could have your HIP calls. You know, if I were to go back and do MCCC again, this would be where we would put the slate calls and those kinds of things. So that is a feature that's supported in OpenMP 4.5, and it's available in ROCm 4 and forward. All right, so we have 2 more applications to cover here. So this team was this was a bit different than a lot of the other applications. So a lot of the applications we talked about already have focused mostly on porting from CUDA to HIP or OpenACC to OpenMP. This team, the Viscous team, was working on putting in some new features into LAMPS, the molecular dynamics code. And it's written, which is, you know, LAMPS is, if you're not familiar, is written in C++, and it uses an MPI plus framework, and the portions that we focused on were the MPI plus Cocos sides of LAMPS. The nice thing about Cocos, much like I was mentioning with Slate, is that all you have to do to run on the new hardware is just get a different build of Cocos that has the HIP backend, you know, in this case, to be able to target the AMD GPUs. So all the API calls stay the same. The source code stays the same. It's just you link to a different library that has the appropriate backend to run on the hardware you're interested in. The sections of the code that we focused on primarily involve particle pairwise interactions and long-range Coulomb forces, as well as some Fourier transforms in conjunction with a Poisson solver that works in K-space. So the initial goals really were to map some of these new features to the GPU using Cocos and optimize both the CPU multi-threaded version and the GPU performance with these new features. There was another stretch goal with this team to look at the PPPM solver, which was that Fourier transform Poisson section of the code. And actually, this is where we did most of the work on the GPU side, with a little bit of low-hanging fruit we picked up on through profiling. Now, on the top half here, on the mapping of the new features, we actually ended up spending a lot of time re-engineering how those new features were going to be implemented. And so most of the work was still sort of in progress by the time we got to the end of the sprint. But I will talk about this last goal here, because there's some implications for folks if you're interested in things like GPU-aware MPI. So that PPPM section of LAMPS, it's a long-range electrostatics calculator. Like I said, it takes basically a Poisson equation. If you take a Fourier transform of that, you end up getting an equation in wave number space that you can then invert. So there's a process to basically map from the way this algorithm works. It'll map from 3D, these 3D arrays that are used in LAMPS pretty much everywhere, to 1D arrays. There's an FFT process that happens, then the Poisson inversion, and then the data is mapped back from 1D to 3D. And pretty much everywhere in this algorithm, when you do domain decomposition on this, there's all-to-all style communications everywhere. And although the majority of the time spent in this Poisson inversion, inside of that, a lot of the time spent on these all-to-all communications. And then the pack and unpack as well, same kind of thing. You'll have, you know, most of the time when you're running in parallel spent in these kinds of communications. So this was for us, an easy low-hanging fruit thing to target, especially when we noticed when we were running this on the on Mulan on the MI100s, there around these MPI calls there was a lot of host to device, device to host mem copies happening, which was suggesting that GPU aware MPI communications weren't happening. And so the easy little hack, and I gotta throw this one to Emily. This is a pretty nice hack. When you're using the Cray compilers, you can set the MPitch GPU support enabled environment variable to 1, and this will force things to use GPU aware MPI, at least on the Cray systems. Doing that right out of the gates gave 1.6x improvement in performance. Just simply cutting out a lot of those host to device and device to host mem copies in between, and just kind of doing the communication as direct between GPUs. I mean, this is one of those things that's just it's important just to look for. I think we all would expect that using GPU aware MPI would do better than without it. I'll talk a little bit about the portability of this approach, because basically once this hack was done, there's a lot of questions still about how to implement this programmatically, so that it's not just like a quick band-aid solution that gets put into a makefile or something like that. Another thing we were looking at, there's in the pack and unpack methods, so they were using the Cocos 1D iteration spaces to do their really triply nested loops. And the 1D iteration spaces is it's just an older feature in Cocos, and there's a new way of doing nested loops called the MD range policy. So this was again another spot where it was interesting to try out whether or not changing from the 1D iteration space to these 3D MD range policies would make any improvement. The reason why you might think that is underneath the hood, when you start doing these things with Cocos, if you have like tile-based access, or if you're doing like little bricks at a time as you're doing these pack and unpack methods, on some hardware it can perform better, some it can perform worse. When we did this transition, we did notice a factor of 2 improvement on the CPU side, so multi-core environments, but there's really no change at all on the GPU side. Now on the GPU aware MPI support, because we saw this happen where out of the box when you run the AMD GPUs, at least the Cocos build system, or not the Cocos build system, the Lamps build system wasn't picking up on the potential that there was GPU aware support on the AMD GPUs. It kind of got us thinking a little bit about whether or not there's support across varying flavors of MPI. So we took a look around, and of course, not everything is consistent, and a lot of the GPU aware features still reference specifically CUDA. So the documentation seems to still be in flux, and it's unclear in a lot of cases whether or not some of these things actually will influence GPU aware MPI on the AMD GPUs. But we do know for sure Cray MPitch is a yes and a yes for both NVIDIA and AMD. And the way you control that is just by using that MPitch GPU support enabled environment variable. And of course, the appropriate Cray programming environment. If you're using MVAPitch, and specifically MVAPitch 2 GDR, you can get support for both NVIDIA and AMD. There's additional stuff you need to define. Of course, during build time, you need to have it enabled when you're building MVAPitch if you're building it from source. But when you go to build your code and run your code, the environment variables you need to toggle on or off is this MV2 use Rockham or CUDA to make that happen. Now, inside of your code, there's also when the MPI compiler with MVAPitch 2 runs through and builds your code, there's the additional CPP flag MPix CUDA aware support in case you wanted to have build options for your application depending on whether or not the system you're building for has that particular support. You get a similar kind of setup with OpenMPI. Again, the CPP flag MPix CUDA aware support is something you can use to toggle on and off regions of code if you need to have your code be portable on some systems that have GPU-aware support, some systems that don't. Now, the hitch is with OpenMPI, it's a hefty build process. You need to, in order to get this to work on AMD GPUs, if you have things outside of Photonics or Mulan, and you're working with OpenMPIs, you actually need to build a tool called OpenACC, and then build OpenMPI on top of that to get that to work with AMD GPUs. So that was quite an interesting thing to learn about here. And we'll move on to our last team, the ASCAP Ops team. So this was actually fairly recent for me. Only a couple weeks ago, I was working with them. This is a radio astronomy code. The original code base that a lot of the mini applications came from that we worked on, it's called YandaSoft, but it's essentially C++ and CUDA. And the bits of code that we focused primarily on Fourier transforms and reductions with complex values. So they came in with 3 applications. And one was called gridding, degridding, and clean. They have very similar footprints in terms of how they access memory and the operations that they're doing. The idea was to go through a process of porting those to the GPU and then take a look at optimizing kernel performance guided by roofline analysis. Now, again, the roofline analysis we did was primarily on the NVIDIA GPUs. We did take a stab at trying to do some instruction roofline modeling, but ultimately we weren't able to make a whole lot of sense of what we were seeing. But we were still quite happy with the progress we made and some of the results we came up with. So, the one kernel I'm going to focus a lot on, because a lot of our attention was given to that one during the sprint week, was this degridding kernel. The way it's structured is there's a single outer loop that has no iteration dependencies. Now, the size of this loop can be millions, billions. I mean, really huge. In some cases, there's too many iterations to fit on the maximum allowable blocks on a GPU. And in other cases, it can be small. But the idea is this is where most of our coarse-grained parallelism is going to come from, is the outer loops. And then there's two inner loops that are essentially looping over small square grids where we're doing reductions. So that's basically the idea. Is we have a GPU block in the outer loop, and the way the CUDA kernel is written and the HIP kernel is written is to do a parallel tree-based reduction over an outer loop. There we go. There's actually a picture of that section of code. So we have this outer loop here where we can do the block-based reduction, and then these inner 2 loops, sup v over and sup u, we can do the tree-based reduction. Now, there's a few versions that were running around during the week. For the most of the week, we were focusing primarily on just doing the parallel reduction on the sup v loop, and then the inner loop was serialized over the threads. And then there's a version you'll see is references version 3 or current in some cases, where we actually did tiled reductions, so parallelizing both sup u and sup v, which actually turned out to be a little bit better. So these are the roofline diagrams generated with Insight on Topaz. So again, you have the memory band, the memory roof, and the blue line there, and then the FP32 above and FP64 roofs going horizontally. Now there's 2 versions actually in here, version 1 and version 2, which we're still doing the just that sup v loop parallelized with the inner reduction loop still serialized. And then the one labeled current here, this blue dot, is showing the basically by tiling that region of code, you're able to increase the arithmetic intensity because you're loading more data out of global memory and into shared memory to operate on in a single go. And so you're able to get a little bit of boost in performance. So I think we're back there. Sorry about that. Yeah, no, I think that was on my side. Sorry, guys. So now, independent of which version of this degridding kernel we look at, at the end of the day, the application is sitting primarily on that bandwidth roof. So there's not unless we really rethink how we're doing the algorithm here, there's not a whole lot more improvement we can do. Now, if we look at this, if we look at a comparison of the runtime of these kernels between V100 and the MI100, if you remember way back in the beginning of the talk here, we showed these two micro benchmarks, or the mixed micro benchmark on the MI100 and the V100. To me, this was a little bit of a surprise, but we do see, if we're sitting on that roof, as you migrate to a new piece of hardware that has better performance, better bandwidth. In this case, since that was our limiter, we do see an increase in our performance. There's some minor changes that I didn't mention here. So in the warp-based, in the reduction, the tree-based reduction we did on the V100s, there were assumptions about the warp size in there being 32. The only other minor adjustment we had to make, in that hand editing portion of the porting process is to get that warp size of 64. Now, it turns out that change, it doesn't really influence a whole lot, as we're talking about a couple clock cycles operating out of registers for that last bit of the reduction. So that bit did not make a huge difference, but really the nice thing is it's nice to confirm, at least in my opinion, that if you do sit on a roof of one vendor's hardware, it seems reasonable that you should suspect that if the other vendor's hardware does better, you should be able to get better performance. Now, there were some oddities that we encountered in this process. I'll briefly mention some of these. I know I'm running out of time. But we noticed, the first kind of few go-arounds when we were timing the application that just things seemed really slow on the MI100s versus the V100s. But if we ran the application multiple times, things started to level out. And, we usually think about this on the NVIDIA hardware where there's like an idling clock speed when the GPU is not being used. And as you start to ramp up usage, the GPU will ramp up its clock speed to some nominal value. And that's the time when you really should be doing your profiling in your comparisons to really get a fair estimate of what the performance of that system can actually be. So I'm showing here first, we saw some issues with mem copies 1, and then I'll show you some examples of some issues with kernel runtimes on both the V100s and MI100s. So on the mem copy side, what we're looking at is on the y-axis here is bandwidth, and the x-axis is the message size that you're sending into the mem copy. We're changing between pageable and pinned memory, and then looking at directionality, host to device, device to host. Now the three different lines you have here. So the pink line on all the plots is Topaz, which is a Gen 3 PCIe with the V100. You have Mulan, which is in blue, which is Gen 4. So we should expect that Mulan would have better performance. And then we have another reference system, which one we have here at our shop, called ORAM. It's another Gen 4 PCIe, but it has the MI50 GPUs in it. And the types of size messages that the ASCAP team was working with was right around the 4 meg size in most cases, which would put us right about here where we could expect, okay, the mem copy performance should be much better on Mulan in any case. If I'm using pageable or pinned, it really didn't matter. Once you get out into that size, the Gen 4 PCIe does give you better performance. So here's a trace profile of the first 6 mem copy calls done in their benchmark on Topaz on the V100s. And the couple spots I've highlighted here, one, the durations, they may mean something. What I find more meaningful here is the throughput. So this is showing, okay, we basically have for those first 6 mem copies, depending on the size of data, anywhere from 4 gigs per second up to 10, which is consistent with what you might expect based on those micro benchmark results and the size of the data you get there. This is all looking pretty good. Now, if we run the same code, the HIPAAfied code with the mem copies on the MI100s, shown on the right here is a trace profile, like visualized with Perfetto, and then an equivalent text output for that. that very first memcopy call is one, if for that same size data. So if I go back, this was 181 microseconds. And on the MI100s, this is now 4 milliseconds, and the bandwidth is, I mean, it's quite terrible. And you can see that same thing in this visual. The hit memcopy, that very first one is just taking up quite a bit of time. So the thinking was, okay, well, does this have something to do with this specific memcopy call? Does it have to do with the fact that this is the first time I'm calling it? So we started running this section of code back to back and looked at successive memcopy calls on the MI100s. So here again is that first memcopy that we do. These ones highlighted in blue are actually the device to host, so going the other way of the same 2 pointers. Again, the bandwidth is quite terrible. And then the second time around, when we do that hosted device copy, we're back in the range that we would expect it to be at, running at about 3 gigs per second. So something else is happening during that first memcopy that caused quite an issue for us, especially since most of our timings initially were looking at regions of code that enclosed mallocs, these memcopies, and the kernel runtimes, which gave us the initial impression that, well, things weren't running so well in the AMD GPUs, but it was really all tied to this initial memcopy that really had nothing to say about the kernel performance. We also see a similar kind of behavior with the kernel runtimes. So we did, again, in this region, we're running things back to back, so we can look at, from the profilers, a range of values for the kernel runtimes themselves. And we see everything on Mulan from 227 up to 507 milliseconds for the gritter. Again, on Mulan for the degritter, it's even more pronounced, 76 to 425, 81. I mean, just all over the map. So as to try to get a better handle on this, Pascal put quite forth an effort to put up a minimal reproducer for this kind of thing. So the way this unit test that he wrote works is that it will essentially run through 2 calls to a very simple kernel that takes up some amount of time, but you just run them back to back. We can do the same thing with mallocs and frees, as well as memcopies, host to device, device to host. So we basically run each of these operations twice, back to back, and look at the difference between those 2 calls. So if we look at that top row here, this is just the kernel launches. So this is 2 different devices, in a multi-GPU system, to see what happens when you spin up one GPU and the other one's not spun up. And then round is for the first, so this would be the first call and the second call on device 0. This column here shows the time taken for Topaz, and the second column shows time taken for Mulan. So that first kernel launch on Topaz, V100s, is 103, and then down to 16. And then on Mulan, you see, again, a huge disparity, 747 to 19. Now, this disparity here, about a factor of 10, is consistent with the ratio of the idle clock speed to the ramped up clock speed on the V100s. This, we don't really understand how to explain. In terms of what we could find, there's no idle clock speed reference for an AMD GPU, although there could be, but it seems to be quite a big disparity in comparison to what the NVIDIA GPUs are actually doing. Down on the mem copies as well, in these particular ones we're looking at, we did not see it on the hosted device copies. Of course, we saw it on the ASCAP team's code, the disparity between the first and second hosted device copy. But here you do see it show up on the device to host mem copy. So you start off with an incredibly long mem copy call, and then you get back down to where it's supposed to be. So I'm kind of running out in the end here, but I do want to thank everyone who participated in these sprints. It was quite a bit of information for me to digest, and of course everyone on the Pawsey support team who helped out is absolutely fantastic.
Thank you so much, Joe. And I think we have time for 1-2 questions. So are there any questions?
So thanks for the talk. Yes, I was chatting with Pascal about sort of this sort of warm-up issue. So if you think about energy consumption, right? I mean, and if you think about energy consumption in the context of like Frontier or something like that, I mean, hopefully, given the amount of money that's spent on the machine, there's probably, hopefully, not a lot of idle time for like, all those GPUs. But I mean, theoretically, if those things are idle, there's really a lot of them. Even the idle energy consumption can add up to something significant. And so, do you suppose if there is like a genuine idle mode for these MI250Xs, that it's really just some kind of like ultra low power consumption mode that really you have to wake up the thing like really from a lot, and so sort of from like an energy conservation issue? I mean, is that a possibility?
I mean, I personally suspect that there's got to be something like that happening. I guess the concern I have right now is that I don't have a straight answer on what's really going on, and there's no metrics we could see from profiling or just from system monitoring that would suggest that the clock frequency changes.
So Joe, just to add the scale of stuff. So I tried the same test on Lumi, right? So the MI250 is there, and instead of, let's say, 500 to 13, it was 5,000 to 13. So there's no way that that's going that much of a rev up. I mean, it doesn't make sense. Literally, the GPU is off almost, and they're like, "Oh yeah, wake it." Well, that's not how the system runs. So there's no way it's that big. And that was with Wacom 5.0.2. And so it's even worse there, but it seems to get better. I mean, normally I don't know if they're exactly the same devices, but there's an AMD cluster that I tried that has 5.2.0, and it's not as bad there. So I'm certain that this is a library issue, but it's a weird one because it's still a very pronounced one.
Yeah, it is. And I can't. So the one thing that still bugs me too is even after doing a few mem copies one direction, you change direction and suddenly the performance is back to being, it's not as bad as the first call, but it's still pretty bad considering I mean, from here to here, from that purple line to the green line, that's the same exact pointers. We're just changing direction.
Yeah.
After, it's just really odd to me that's happening. It would be helpful to know, but I think at this point for me, it's one of those things. It's like, all right, I know it's happening, don't know why, so it's just more of a functional bit of knowledge at this point.
Thanks, Joe, again. And Anne already mentioned that throughout the event we have heard your name a couple of times, and very positive feedback from all the sessions that you have run so far. So you'll hear from us. We know that you are a very busy person, but we'll be looking at getting some more of your time very, very soon. So thank you again for your presentation.
Thanks, you guys.